angle. Any angle can be figured out this way. Let's take a look at a milling example. First of all, the mill coordinate system is if you're standing in front of a milling machine, like picture a Bridgeport, sideways is always called the X direction. The numbers get bigger in that direction, and I have it laid out that this will represent 0. This is a 3-inch dimension, and this is a 4-inch dimension. And this direction, the in and out, looking at a machine tool, this would be the X, and the in and out would be the Y direction. The numbers get bigger, the numbers get smaller. And I have it laid out that I know that this is 2 inches. But what I don't know is I don't know what this dimension is right here. So I need to figure this out. Step number 1 is you draw a triangle. Just go over here and draw a triangle that looks like the triangle we have here in this part. That's our triangle. Now this angle right here is 15 degrees. And if the two small angles add up to 90, then this must be 75 degrees. Now I look for a known dimension. Overall this is 4. This starts at 3. This must be 1 inch. So I have this right here. Now this is what I'm going to use now. I'm going to use this little formula again for figuring this out. I'm going to touch on my calculator in this order. The angle, in this case the 15-degree angle. Then I will touch the tangent key times the adjacent side equals the opposite side. Now let's go back there and do it. And on my calculator now I will go through touching the keys in the proper order. It will be 15 tangent times 1 equals, and it is 268 thousandths. This side right here is 0.268. Now I go back to my part and I look at this. This is 268. The part overall is 2 inches. So this must be 1.732. To double check it, it would always be good to double check it on your calculator. Now we'll go 2 minus 0.268 equals 1.732. Okay, so this is my dimension. And now typically, using cutter compensation properly, I can now put my tool to this position, actually tell my tool to feed to this position right here. Cutter comp will feed it, hold it around it, go to this position, just program the actual part dimensions all the way around my work part right now. That is the use of math for CNC lathe and CNC mill programming. Let's do an example of what an actual mill program would look like. Just the motions right now, using the numbers we've just figured out. I would be coming, in order to mill around this, I would be coming somewhere from this direction. And I would be setting my cutter compensation, which we'll talk about later. But what it would look like is something like this. This motion from here to here would set cutter compensation, and it would say G0, that's a rapid motion. And cutter comp is a G code. This would mean cutter compensation to the left, because all this happens around the left, the cutter to the left of the work part. G41 would set that. There would be an H value where the cutter comp is registered, let's say H21, and all this would go into effect to this dimension. And that dimension is X0 and Y minus something, how about 0.5? I would now be sitting in cutter compensation ready to cut. The first cut is G1, that's this motion going up to a Y dimension. The Y dimension is the actual part dimension of 2 inches. I would also have to figure out my feed rate for this. And let's assume the feed rate is 10 inches. That would actually get me up to this point here, past the work part, aligned to this line. The next line is X3. cut of compensation would figure out the proper tangent point right here, that I'm aligned to this angle. Now the angle itself would look something like this. It will go to x, the part dimension of 4, and in the y direction, it will go to the dimension we had figured out earlier, 1.732. So we always have to figure out the dimension of a part from the angle given. So this is the right dimension. Now to go from here to here, it would just go y 0, because this down here is 0, but actually we're past it. And now the line going across from here, so we went here, we went here, we went across here, we went down to here, and now this line I want to feed right past my work part by saying go to x minus something. How about 0.5? We would now be sitting along this line, still in cut a comp, and usually the next line feeding in this direction would be a line that says G0, and this is the code for taking cut a compensation out. You know, it's put in properly, and this is the way you take it out properly, by going to x minus a bigger number. How about 2 inches? So there is an example of figuring out a part shape and then actually putting it into a programming format. Let's assume we have a machine tool that does not have the feature of nose radius compensation. Nose radius compensation in the lathe would mean that when we program a shape that looks like this, we program the actual intersection points. We program this, and we program this dimension and this dimension right here. And our tool will go from here, not to here, but the control itself will have the ability to put a tangent to this. So the actual program dimensions are the dimension of 1 inch and 2 inches and whatever these diameters are, but the control will have the ability to actually figure out a tangent point, something like this, where the part of this tool here has to go where it is tangent to this angle all by itself. But suppose we don't have that feature, and that feature is normally called G41 is compensation left, and G42 is compensation to the right, and G40 is cancel compensation. Now, this feature has been available since about 1980 on most of the Fanuc controls, since the advent of the 6 series control, the 6T control, or the 6M control. What that would just mean is turning and milling. Prior to that, there were many, many, many controls, and there's still many, many controls in use in many machine shops that don't have the ability to do this sort of thing. They don't have the ability to do compensation by themselves. So we have to figure it out. And let me just give you an example of what this would look like. What it would be covered, though, is in a video that is called Supplemental Math. Now here's a lathe part that would be made on one of the older controls. And this right here, this could be the Fanuc 5T control. And basically all these controls here are pre-1981, 1980, 1979, somewhere around there. The Fanuc 5T, there was a Yasnag 2000 control, the 2000 series. Many of these older controls, we had to do something like I'm going to show you right now. First of all, the part is all laid out. This is a 2-inch part, 1 inch right here. There's a 30-degree angle that runs across here. The dimensions are properly figured out. This is 1 inch, this is 1.866. And if we want to have a 1/4 inch radius right here, then that would start at a diameter dimension of the radius taken off the 1-inch dimension times 2 because this is per side. This is always diameter programming. So if we take this radius off this number, this dimension becomes 0.5 as a diameter. This dimension is 1/4 inch over. This would be a minus dimension. So is this, so is this. Now, those are the right part dimensions. But remember, we don't have the feature of nose radius compensation. So here's what we're going to have to learn to do. We will have to learn to put this typical tool, this typical 1/32 insert, which is really about 31 thousandths, but we could round this off to 30 without causing any really important error in our actual radius. The error would be so small that you can't really figure it, you can't really measure it, if we use 30 thousandths here for nose radius compensation. Here's what we would do. We have to put that tool into this position. We cannot actually program this dimension. We'd have to figure out where that tool goes in order to get the center of this tool onto the tangent point where this radius starts. Same thing here. We have to figure out this dimension. So right here, we'd have to figure out an adjustment for this dimension. And then as we swing around, we have to figure out an adjustment for this dimension. At this point, we have to figure out the tangent point between the tool and this angle. So there's an adjustment right here. And then as we cut up in this direction, we would have to extend this angle and figure out the tangent point where this ball meets the extension of this angle, and then we just go across. Typically, whenever we don't have a straight line, across here we actually program this dimension. Across here we program this dimension. But anytime we come or meet a radius or an angle, we have to figure out an adjustment based on the size of this little nose radius. And let's take a look at that, and we'll actually write a program. So what we have here is then a lathe example for one of the older controls where we have to make corrections whenever we meet a radius or meet an angle, and it would look something like this. We're assuming we're starting up in this direction here, and this is line number 4 that starts to feed up in this direction. And we're telling it to go to the actual part dimension. But what we have to do is, we have to figure out that we need to correct this. The center of this nose radius, this point right here, has to go to the 0.5, and that means that the edge of the tool, which is what we're actually programming, we will be programming this edge and this edge right here in a turning tool. That edge has to be 30 thousandths per side below this number. So we would have to figure that out. Now as we swing around, we would have to put the center of the tool again on this dimension. That means we have to correct this dimension as we swing around. The actual code here is the G3 that will go to X 1.0. That's this dimension. But this Z dimension has to be corrected by the amount of the nose radius right here. So the nose radius here is down per side plus here over per side, but only one time. And also, the definition of a radius on the older control was entirely different, and we'll be covering that in the 5T programming. But what it would look like is that we're actually defining the distance from the center of the tool to where the center of this radius is located. That was this K value. That has to be corrected. Now we have gone around, and now we're going to here. This has to be corrected by a value that's equal to this 30 degrees. And it happens to be approximately 24 thousandths right there. Also, as we go up here, it has to be corrected. So, you just have to remember, if you have one of these older controls, you have to go through these steps in order to get your right part dimension. Now, this is the subject that would be covered in supplemental math. And it will only apply if you have an older control. And there are still a lot of these controls around. The last subject leads right into programming the older lathe controls. In this case, let's take a look at programming the 5T control. Most everything that we're going to do here on this 5T control will also apply to the later controls, to the modern control. Now remember that this control, this 5T control, was just before 1980. This control was on many different types of Japanese machines, and there's still many machine shops that would be using this control. Most everything will apply to the newer controls. To begin with, we would have a tool number. We would also have to figure out our tool position. What I have written down here is I have 6 inches here. That would mean that this tool is sitting at a diameter of 6 inches when we start this program. And we would have to learn on this control and also on the 6T, on the later 10T control, how do we get that tool actually to that point when we hit our cycle start that we're really there. And that would be done through coordinate system setting. It would be covered in the actual lathe programming course. So we're sitting at a 6-inch diameter value, and we're sitting at a 4-inch diameter value. And what a 4-inch distance value from here. This is the diameter, and this is the distance from the finished face of our part over. The part itself is 3 inches, and this is 1018 steel. That's mild steel. All I'm going to do here is I'm going to take a finish cut. I'm going to go from here to a point up here and take a finish cut across this face. I'm assuming that we have about 30 thousandths of material across this face. So I would like to get to a point, to a logical place here, and then face across and then just stop. And I'll have to figure out my RPM. This is 1018 steel, that's mild steel. On a finished cut, we can run somewhere around 600 surface feet. So if we go surface feet times 4 divided by the diameter, it would be, if this is 600 surface feet, it would be 600 times the constant of 4 divided by the diameter of 3. The reason that I'm figuring this out is that these older machines did not have, many of these older machines did not have constant surface feet. They could not figure out their own RPM. I had to figure it out. So in this case, this is 2400 divided by 3. The speed would be 800 RPM. This is my RPM value here, 800. That will show up later in our program. The feed rate across here, let's say I feed somewhere around 10 thousandths, it would look something like this. This is my F value, 0.01. But there'll be some differences here. I really can't write it down like this. Our typical program would look something like this. Then in our first line, in line number 1, this did not have a program number. We just had line numbers. We normally started with line number 1. There would be a code that would look like this. It's called G50. And the dimension following the G50 would be the dimension of where this tool is sitting. It is sitting at 6, and the number had to be written out longhand. One of the major differences between this and the newer controls is that I could not write decimal point numbers. I could not write X 6.0. I would have to write it out longhand in tenths. 1, 2, 3, 4. That would mean 6 inches. And into that same line, I would put the Z dimension, and the Z dimension would be 4, 0, 0, 0, 0. If you actually program one of these machines, it's very important that we write the numbers out in tenths, because with one digit missing, it starts reading from the back forwards, and it would read that as 600 thousandths. Everything has to be written in tenths. Now the control knows where that tool is located. The G50 means I am telling it where that tool is located. It is sitting at 6x4. It is up to us to make sure that that tool is really there. Because if that tool is not there, it will just count from wherever you are and either run right into the part or miss the part completely. So you have to be at 6x4 if you're telling the control that it is sitting at 6x4. That would be our typical first line. Our typical second line would look something like this. Now, the speed could not be given in surface feet. So one of the methods of giving the speed would be to give it as an S value directly. It could be S, and we figured out 800. And M3 would start the spindle. The spindle is now running at 800 RPM. 800. Now, it is very possible that these older machines did not have this capability. They may not have a DC motor. They possibly could have a gear range. So the possibility exists that you have to pick the closest gear range to the number that represents this. For instance, it could be given like this: S1, S2, S3. And each one of these would stand for a certain RPM. And let's say that this here represented 750 RPM. Very likely that would be the closest you could get to 800, so you would have to program this S3 value. But that would depend on your particular machine. If the machine had a DC motor, they usually had an option where you can program the actual RPM. Into this line we could also put our tool number, or after we start our spindle, we would just give our tool number by itself. And the tool number would be programmed just as it is today by just giving the actual tool number. This number here, T0101, would call for tool number 1 along with tool offset number 1. And the order in which these are given is not that important. We could really start with the tool number and then follow that with the G50. Normally we start with the G50 and then we possibly have the tool here and the spindle speed here. But overall, eventually, we have to get this information in there. It's absolutely important that if we don't have an actual spindle speed called for, of course we won't have a spindle speed. If we don't call for a tool number, then of course we will not have a tool. Okay, now we have all the information necessary to be able to go to this point by saying in line number 4, we would like to wrap it somewhere. G0, same coding as today. On very much older machines, we have to write G00, but usually G0 is sufficient. Now we figure out where we want to go. We'd like to go to this point. Well, if this part is 3 inches, we would tell it to go to X, a number a little bit larger than 3 inches, written without a decimal point. 3/200. 3 inches and 200 thousandths is a number larger than 3, and we're not hitting our part. At the same time, we go to Z0. That would represent the finished face of this part. Now we're sitting in a logical place to face this part. To face the part, we would say that in line number 5, we would like to use a G1 code, just as today. The motions are the same in the older controls. An S is still an S. An F is still a feed rate. M3 is the same. The G50 is the same, carrying much, much closer to today. So we're saying here G1 feed. To where? How about the center of the part, which represents X0? This tool would now actually be sitting in this relationship. It's not quite all the way to center, but usually that's close enough. And we need a feed rate here, an F value. And let's say that we said earlier that we would like to feed at this feed rate. So that feed rate is correct, except we can't write it with a decimal point. So written in tenths, 100, that would represent 10 thousandths. We're here now, the part is basically finished. So in line number 6, we would say wrap it back to where we came from, to X6 with our 4 digits and Z4 with our 4 digits, and we're finished. Possibly we have turned the colon on earlier in this line. That would be the same code as today, that's M8. And at the end of all this, in line number 7, the M30 code shut everything off just as it does today. Basic difference between the older control and today, we have to write everything out longhand. It didn't have many of the features. It didn't have nose radius compensation. It did not have constant surface feet until very, very late on a few machines. Feed rates had to be written out longhand, again without a decimal point. But the overall programming procedure was pretty much the same. It was diameter programming. We told the control what to do one step at a time. And that would be the method of programming the 5T and other controls. There is a Yasnag that was on a lot of Moriseki's. A Yasnag 2000 was programmed like this, and many other controls. There are a couple of possibilities that you should be aware of. Certain machines where these numbers, all the diameter numbers, had to be written as minus numbers. On the early machines, there were turrets in the front and in the rear. Typically, if the turret was in the front, that was the positive side. If there was a front and a rear turret, the rear turret would be written as a negative number, both for the G50, right there, also for all the dimensions. All dimensions, all actual part sizes would have to be written as negative numbers. There was no program number on this. We started out right with this N. And if you had more than one program in the memory, you could start your first program at N1 and start your next program with N100. You know, that represents the older method of programming, and now we'll go on to the more modern method of programming. Before we get to what's called the modern CNC control, let's take a look at some of the reasoning, some of the control numbers and so forth. In 1981, late 1980, Fanuc came out with the 6T control. Now since then, we have gone through a series of numbers. There's been a 10T, an 11, and right now on machine tools, on new machine tools, you would see the 0T and the 15T. Now the nice thing is that from here through here, this would be 1992 right now, the programming method that was established for the 6T control has changed very, very little. The same method is basically used all the way through, with very, very few exceptions. And other controls follow the same programming system. Fanuc is very, very strong in this control market. The 6T and the 6M. The 6M would be the milling machine, also runs all the way through today. So there would be a 15T and a 0T and also an M for both of these. Now other controls use the same programming system as the Fanuc control, and other controls today, there's a machine tool manufacturer that's called Fidel that makes a very nice machine, and they use the same method of programming. There's another American machine that's called Haas